Welcome back, and in this last section of the notes we're going to be looking at metallic bonding. So that's the electrostatic attraction between the metal cations and a sea of delocalized electrons. We're also going to be looking at a little bit of a comparison between the three types of bonding we've had a look at so far: ionic, covalent and metallic. So we're looking at metallic bonding. So that's the electrostatic attraction between these positive metal cations and a sea of delocalized electrons. And it's the bonding you find most predominantly in the periodic table, as most of the elements are metals. The metals of group 1, the alkali metals, lose 1 electron, group 2 lose 2, and group 3 lose 3 electrons. So again, we come back to the same idea of size and charge. In this case, the strength of the metallic bonding is dependent on the number of electrons which can be delocalized and also the size of the cations. So the larger or the greater the number of electrons delocalized, the stronger the bonding is going to be, and the smaller the ion, the stronger the bonding is going to be. We can use this to explain the difference in melting point between metallic elements. So if we look at the first pair, sodium and potassium, well, they're both in group 1, so they both delocalize 1 electron, but the sodium has a smaller ionic radii. So the sodium has the stronger metallic bonding. Comparing sodium and magnesium, sodium again group 1, but magnesium is in group 2, so it will delocalize 2 electrons. It'll also form a smaller ion than sodium. So in this case, it's magnesium which has the higher melting point. Magnesium and aluminium, again, aluminium is in group 3, delocalizes 3 electrons, and again forms a smaller ion. So that is the one with the stronger metallic bonding. It all comes down to size and charge. Remember, smaller, more strongly charged, stronger attraction. So we do need to make sure we're making some sort of comparison. So the sodium has a smaller ionic radius, but the same number of delocalized electrons as potassium, therefore more energy is required. Magnesium, smaller than sodium, and contributes more electrons, so more energy is needed to overcome those forces of attraction. Aluminium, smaller ion, and again more delocalized electrons. It's important in these that you make some sort of comparison in your answer, so more than, smaller than, and so on. So they're good conductors of electricity and heat because these delocalized electrons are free to move, and they can move a hot area to a cold area, taking that kinetic energy with them. It also explains why both the electrical and thermal conductivity increases as you go from sodium to magnesium to aluminium, because you've simply got more delocalized electrons. Therefore, you've got a larger current. On the last page of the notes, we're going to divide the following into metallic, covalent, or ionic. And there you can see I've done that for you. I've also circled any of the giant ones and underlined any ones which conduct electricity. So in the ionic, they're all circled as they are again in the metallic, because all metals and all ionics are giant structures. I've underlined again them all in this section because they all conduct electricity. I've got a dotted line across the magnesium oxide because it only conducts electricity as an aqueous solution, and magnesium oxide isn't particularly soluble. I've also underlined graphite. That's the only covalent one which conducts electricity. You might be surprised to see that I've not circled water. Water does not conduct electricity. You might have seen that you might have thought that it does, but it's actually the dissolved salts in the water that conduct electricity. Pure water itself does not conduct electricity. but as you can't usually get pure water, it will conduct electricity due to dissolved sodium or chloride salts that are in the water. Even rainwater has some dissolved salts in it, but pure water would not conduct electricity. So that finishes this section of the syllabus, looking at the three key types of bonding: ionic, covalent, and metallic. The key thing that you need to remember is size and charge. So the smaller something is, the more highly charged it is, the more attractive it's going to be, and the stronger the bonding. And it doesn't matter if we're talking about metallic, ionic, or covalent, the same rule applies. It all comes down in the end to size and charge. So until next time, take care, stay safe, bye bye.